Welcome back. So today we're going to be talking about applications of the quantum Fourier transform. In particular, we're going to be mostly focusing on the applications of the quantum Fourier transform to arithmetic. The main reason why, you'll notice in the syllabus that I was suggesting that we would cover the quantum phase estimation algorithm, not the iterative quantum phase estimation, but the Fourier-based one, before talking about arithmetic applications. After going through the notes a little bit myself that I had, I figured it might be actually a little bit easier if we start with a simpler application of the quantum Fourier transform before going to something a little bit more complicated like quantum phase estimation. So we're going to begin by building a quantum adder. Now, this quantum adder is known as a Draper adder. It was, originally come up with by a guy by the name of Draper, and the idea behind it is that what we do is we use Fourier duality to turn the problem of adding two numbers together into the problem of doing a pair of Fourier transforms and a bunch of controlled z rotations, effectively. So that is the idea. Since you've already seen all of these components, the construction for this form of an adder is very straightforward. This is relevant because many natural quantum subroutines that we'd come up with require arithmetic in one form or another. And so, this is now not the only way that we can do arithmetic on quantum computers. There's methods such as singular value transformations and linear combinations of unitaries that can be used in order to implement transformations without explicitly doing arithmetic. Many quantum algorithms will use this approach because of the fact that it's relatively efficient and it doesn't use that many qubits. In fact, actually, this approach uses literally 0 qubits in overhead if you actually need to add numbers and store them in a bit register. So that's what we're going to be talking about right now. And so in order to get a better idea about this, let's just jump right in. So if you recall, from last lecture, we talked about the quantum Fourier transform, or QFT. And the basic property of the quantum Fourier transform is on n qubits, f2 to the n, is a unitary matrix that implements the discrete Fourier transform on that space. And what it will do is it'll take a computational basis state labeled J and map this to 1 over square root 2 to the n, sum of k equals 0 to 2 to the n minus 1, e to the 2 pi I over 2 to the n multiplied by j and k, acting on k. So note that the probability, if we were to just apply the quantum Fourier transform and do something like the following, we put jn and we apply f2n coming out, and we measure over here, the probability that we get measurement outcome L is just equal to L f2n j absolute value squared, which, of course, is equal to 1 over 2 to the n for all j. So what this says is that basically, what we do with the Fourier transform is we take all the information which would have been in the bit string, and we move all of that information into the phases that we end up getting on this state over here. So that's the idea, is that the quantum Fourier transform allows us to go from a bit representation of a number, in effect, to a phase representation of the number. Now that we have this as a phase representation, we can actually use our tricks to manipulate these phases in order to transform this back into a modified bit value. And that's how the adders end up working. So in order to be able to do this, what we're going to need to do is we're going to need to first build an incrementer. So the first thing, just so that we can focus on the essentials, I'm going to assume that we have a unitary U. And this magic unitary has the following property. It will take a state k and map that state to e to the 2 pi I k divided by 2 to the n, acting on k over here. So that's what this operator u ends up doing. The reason why we care about it is the following. Let's take a look at the following subcircuit. F 2 to the n dagger, which is the inverse of a Fourier transform. Then u f2 to the n, acting on a state j over here. Okay, so this is equal to u 2 to the n at sum of k 1 over root 2 to the n e to the 2 pi I j k over 2 to the n k. All right, great. Now, by using linearity, we can act with u on this. So this is equal to f 2 to the n dagger 1 over root 2 to the n sum over k e to the 2 pi I j k divided by 2 to the n. Now, where I'm going to use the definition of u in order to get e to the 2 pi I k divided by 2 to the n, acting on k. All right, great. Now, if I put this together, this ends up yielding 1 over root 2 to the n sum over k e to the 2 pi I over 2 to the n k j plus 1 k. And this is really cool, I think, but admittedly, I'm a little bit easily excitable. This we can end up writing as f2n dagger f2 to the n j plus 1. And this is equal to j plus 1. Now note that there is one thing that I haven't fully described. If this j plus 1 ends up giving a value over here greater than 2 pi, then the phases will wrap around. And so this ends up actually causing the adder to be modular. So technically speaking, it's j plus 1 mod 2 to the n that we end up getting out. Okay, great. So now, this ends up giving us a modular incrementer, because a modular incrementer should take a value j and map that to j plus 1 mod 2 to the n. So just to be clear, exactly what's happening here, if we imagine we start off with 0, then it will take us to 1, then it'll take us to 2, all the way down to 2 to the n minus 1, and then the next step will take us up to 0. Okay, so that's what the modular incrementer does. The only question that remains is, what the heck is this u operator? So let's talk about how we can end up building u. Now recall, u has the property where u acting on k is equal to e to the 2 pi I over 2 to the n k. All right, so that is the operator u. Great. Now, the next step is let's consider building this. We're going to build this using a technique called binary exponentiation. And the way that this ends up working is, let's consider k just to be a binary expansion. So I'm going to start with the most significant bit. I'm going to call it k1 times 2 to the n minus 1 plus k2 times 2 to the n minus 2, going all the way down to kn times 2 to the 0, or 1. But you see the pattern. All right. So if that's the case, now let's do it. Let's do a binary expansion. We can end up writing, if K is a computational basis state, this is just going to be, by definition, the tensor product of K1, K2, going all the way down to Kn. Just like if we had, let's do a simple example. Let's say we do 5, right? That's equal to 1, 0, 1. That's equal to 1, 0, 1. And here, this would be K1, this would be K2, and this would be K3. Okay, so you see the idea behind this. So now, let's end up defining another operator. I'm going to define an operator RQ for any Q to be equal to the following. 1, 0, 0, e to the 2 pi I divided by 2 to the n times q. Now, this, you'll note, is actually equivalent to RZ of, what would it be? It would be, well, actually, I think it's just RZ of 2 pi I q over 2 to the n. Okay, up to a global phase. Now, the reason why I'm not using RZ, and I'm using this over here, is because we're going to need a controlled version of this. And recall that controlled rotations of this form and controlled rotations of that form are not equivalent up to global phases. So I did this just to specify that I mean, when I'm talking about doing a controlled phase rotation, this kind of phase rotation, not that kind of phase rotation. Okay, great. So the circuit that I'm going to propose is the following. Let's imagine we're doing a binary decomposition of the input value k, going all the way down to k to the n. So what we end up doing is we end up doing the following. We will put in r 2 to the n minus 1 here. We'll put in r 2 to the n minus 2 here, and we'll put in r 2 to the 0 there. Great. So this is our circuit. Now, let's pay attention to what this will end up doing. So if we have our input state over here, it will end up mapping this to e to the 2 pi I k 1 times 2 to the n minus 1 over 2 to the n, k1, times e to the 2 pi I k2 times 2 to the n minus 2 over 2 to the n k2, so on and so forth. Now you might wonder, hey, where the heck do these k1s and these k2s come from in the exponent? Well, it just comes from the fact that if we apply RQ to a computational basis state x, this will end up yielding e to the 2 pi I x q over 2 to the n x. Note, there's two cases. If x is 0, then this is 1. And that corresponds exactly to the value of RQ that we require. However, if x is 1, then we end up getting this value. So this, again, is just a compact way for us to describe the phase relationship that we end up getting out of this RQ operation. So now that we have this RQ operation, let's put this in and evaluate what this circuit ends up doing. So the output ends up becoming e to the 2 pi I over 2 to the n times k1, 2 to the n minus 1, plus k2, 2 to the n minus 2, going all the way down to kn, 2 to the 0. And I'll just group all of these things together again as k. Now this, if you recall from the binary expansion for k at the top over here, this is e to the 2 pi I divided by 2 to the n times k. And that is equal to uk. So you see, this sequence of rotations going over binary powers of 2, this is one of the reasons why it's called like binary exponentiation, is a direct way for us to implement e to the I k over 2 to the n, or u. Okay, so that's how we build u. Now, the next step in the construction, or almost like a quest to build an adder, is to do a controlled incrementer. Okay, great. So how do we do this? Well, the simplest way of building a controlled incrementer is as follows. Let's say we've got j down here. We begin by applying the quantum Fourier transform on n bits. Then what we do is we do a controlled u operation, and we undo the transformation over here. Okay, so this over here, we can very quickly see that this will yield a controlled incrementer, as in, for every input, it'll end up yielding x and j plus x mod 2 to the n. All right, cool. To see this, let's do case analysis. Let's say x equals 0. Then we end up having 0j maps to f2n dagger f2n j. The reason why is that this controlled unitary never fires. So that's equal to j. Now, if we look at the case where x equals 1, then this 1j is now going to map to f2 to the n dagger u f2 to the n j. And as established, this is equal to j plus 1 mod 2 to the n. Wonderful. Okay, so now if we take a look at this in both cases, just like we did before, this ends up yielding, I guess I should put a 0 and a 1 in here, 0, 1. This pattern is exactly equivalent to xj goes to x j plus x mod 2 to the n. Great. So we've actually built more than just a controlled incrementer here. What we've built is a 1-qubit adder. So if we have a single qubit and we want to add it to an n-qubit register, we can use this in order to be able to build it. Okay, and so actually we're a good chunk of our way done towards building a general adder. In order for us to build a general adder, we're going to need one last piece of technology. What I'm going to need is I'm going to need a gate. And I'm going to need a gate that I'm going to call add 2 to the p, let's say. And the idea basically is that what this ends up doing is if we've got a state j coming in here, what we're going to get is we're going to get j plus 2 to the p mod 2 to the n coming out the other side of this adder. Great. So let's figure out how we did this. Now, the way the incrementer ended up working, if you recall, is we needed to be able to build an object such that when k is input, it 2 to the e to the 2 pi I k over 2 to the n phase is added back to this. So now we want to actually do something a little bit more than that. What we want to do is we want basically to be able to do this 2 to the p times. So what we would like to do is we would like to implement this through the following. We would like to be able to do something like f 2 to the n over here. Now we put this through a u 2 to the p, and then follow it up with an f 2 to the n dagger. Now, at first glance, this really doesn't look terribly efficient, because if p is even a modestly big number, we would have to apply this u circuit a ton of times in order to be able to do this. However, actually, this isn't anywhere near as inefficient as it seems at first glance. Recall that u can be implemented by a circuit of the form r 2 to the n minus 1 going all the way down to r 2 to the 0. Okay, great. So then in that case, what we need to do is we need to simply take a look at what these rotations are. Because these are all products in here, we can actually just replace this all with r 2 to the n plus p minus 1 going all the way down to r 2 to the 0 plus p, or equivalently, just 2 to the p. Okay, and so you can see for the case where p equals 0, we end up recovering the same old incrementer that we had before. Awesome. Okay, so this 2 to the p ends up reducing down to something of exactly the same complexity as the case where p equals 0. Awesome. So now let me just verify that this ends up doing exactly the same thing. So going through the totally same analysis that we had before, we have that f2n dagger u f2n for the Fourier transform acting on an arbitrary input state j over here ends up giving us the inverse Fourier transform over here of u acting on 1 over square root 2 to the n sum over k e to the 2 pi I j k divided by 2 to the n k. All right, great. Now we're going to go through and we're going to do the same binary expansion and recompression trick, and we end up getting that this is f 2 to the n dagger 1 over root 2 to the n sum over k e to the 2 pi I k over 2 to the n. Now we're going to get j plus 2 to the p this time, acting on k over here. Now identifying this as f2 to the n dagger f2 to the n acting on the state j plus 2 to the p, we end up getting that this is just equal to j plus 2 to the p, again, mod 2 to the n. And there you have it. So the controlled version of this, I'm just going to denote as follows. Okay, now that we have this, we are actually almost all the way towards where we need to be in order to be able to build a arbitrary adder circuit. So the reason why is, again, if we have x j over here, we end up mapping this to x j plus 2 to the p x mod 2 to the n. Okay, so now we are just about ready to build an adder. So the way that we end up doing this is let's consider the simplest adder that I can think of. So let's consider an adder that is xy maps to x y plus x mod 2 to the n. Okay, cool. So note that actually this process is reversible for assuming that x and y are n-bit numbers, because everything will have a unique additive inverse in this. So, okay, the way that we're going to build an adder out of this is just by noting what x plus y is. Okay, so we're going to begin by writing x is equal to x1 times 2 to the n minus 1 plus all the way down to xn 2 to the 0. Okay, great. So, therefore, x plus y, that is equal to x1 2 to the n minus 1 plus x2 2 to the n minus 2 plus all the way down plus y. Okay, so I can end up writing this as x1 2 to the n minus 1 plus y plus x2 2 to the n minus 2 plus x3 2 to the n minus 3, so on and so forth. Now, this ends up giving us a convenient way that we can end up doing this. This is actually just given by a controlled add 2 to the n minus 1 gate. So, if our input string is of the following form, x1, x2, going all the way down to xn, and our qubit string, note that this is n qubits here in this diagram. First, we begin by doing a controlled add of 2 to the n minus 1. Then we're going to do an add 2 to the n minus 2. And then we're going to do an add 2 to the n minus 3. Oh, sorry. This has gone all the way down to 0. Add 2 to the 0. Okay. And that circuit implements this, which ends up giving us our modular adder. So let's figure out what the complexity of this is. Now, the complexity, I should mention, this can actually be simplified greatly. One of the reasons why is because if we take a look at the U operation that we defined previously, what happens with the U operation is that actually phases can wrap around many times when we're looking at the add circuit. So for example, if this thing up here ends up taking a form 1 e to the 2 pi I over 2 to the n times 2 to the n plus p minus 1. Okay, cool. So now, let's say that we're dealing with a case where p is greater than 1. If p is greater than 1, then e to the 2 pi I 2 to the n plus p minus 1 over 2 to the n is equal to e to the 2 pi I 2 to the p minus 1, just canceling that and that. And this is now an integer. And so this has to be equal to 1. So for all integer greater than 1, this actually acts as the identity. So the cost of doing this operation is actually only 1 r 2 to the n minus 1 gate. So that ends up dramatically simplifying it, but that only leads to constant factors. So in order to upper bound this cost, we can say that each of these adds over here is a circuit that is of the form f2 to the n u f2 to the n dagger. Okay? This operation u in the middle, as established, contains worst case scenario order n R2K or controlled R2K operations. This consists of, well, just one FT, which we discussed last time, can be implemented using order n squared single qubit rotations and entangling gates. So this also is order n squared. Now, if we take a look at how many of these operations we have, we've got n different steps in here. The thing is that these different steps are going to end up creating operators that end up looking like the following. Some sort of control going up here, and f2n dagger over there, f2n. And so you can see that the Fourier transforms are going to telescope in between all of the adders over here. So the total number of FTs is equal to 2, and the total number of CR2, the number of CR2 to the P or whatever is going to be equal to order n squared. Okay, each of these can be decomposed into order 1 fundamental gates, as in Hadamard, RZ, and C0. And we showed that before, remember, with the controlled swap trick. Okay, so using that construction, we can implement this using order n squared operations. And so the total cost of this adder circuit is order n squared fundamental operations. The number of ancilla qubits, now in part it depends on how we end up doing these controlled operations in here, but the number of operations that we can do if we use a trick that you derived in homework 2 is equal to 0. So there's no extra space required for doing this. And this is a very, very nice property because qubits are hugely expensive, at least on near-term quantum computers. So coming up with tricks to reduce the number of qubits that you need for operations is really nice. So that's one of the reasons why this approach is so cool, and also because of the fact that unlike most other forms of arithmetic that you could consider doing on a quantum computer using AND gates and the like to perform a decomposition, this version doesn't really have a strong classical analog. So it's a wonderful example of using quantum intuitions and quantum operations to be able to do something, at least in a slightly different way from the conventional approach to how you would do it on a classical computer. So that is how we can end up doing adders on it. And once we have an adder, then what we can do is we can implement transformations like this. We can build a multiplier just by following the school book multiplication algorithm and yield following x times y mod 2 to the n. All right. Now, with addition and multiplication, what we can do is we can implement any polynomial function of x. And in turn, any continuous function can be approximated by a polynomial of fixed degree. And so what this ends up doing is this gives us a way to be able to build an arbitrary transformation on bits in a quantum computer by using this adder circuit to build a multiplier, and then using that in order to implement a polynomial. So this is one of the reasons why this type of reasoning is so important, because it gives you a direct way in order to be able to build all of these arithmetic operations that you would ideally like to do to say something like, a transformation that stores a qubit x and maps that to x e to the x, say. This you could end up doing once you have an adder, or at least a good approximation to e to the x over there. So that is how you build an adder. Now, let's go on to the next application. The next application is quantum phase estimation. Okay? So the idea behind quantum phase estimation is actually really kind of straightforward. So the idea is, let's begin by building our intuition up through a number of cases. Let's take the example of the most trivial quantum phase estimation algorithm that we can do. This quantum phase estimation algorithm is of the form 0 up here. Now we're going to do a controlled Z over here, and Hadamard again up there. And let's assume that we have a state down here, V, such that, or actually let's just say it's 1, so that Z acting on 1 is equal to minus 1. Great. Now, the way that we can end up building this is the following. What we do is we first begin by noting that actually this whole thing can be simplified. This circuit actually is the same thing as that. And so we'll note that if we've got a 1 down here, then it'll map to 1, 1 up there. But if we have a 0 down here, then this ends up mapping to 0, 0. So this bit over here gives us the one bit representation of the eigenvalue, which in this case is minus 1. All right, cool. So now let's do a slightly more complicated case. Let's say what we want to do is we would like to be able to figure out the eigenstates of the S operator, where S is equal to, again, 1, 0, 0, I. Okay, great. So now we're going to need a little bit more machinery. The reason why is because this phase over here is of the form e to the 2 pi I over 2 times v, where if this input was v over there, this would be the two eigenphases that we end up getting out. Now we need something that's a little more subtle. We need our eigenvalues to have twice as much precision. So we are going to want them to be of the form e to the 2 pi I over 4 times v. And we need this because this is equal to e to the pi I over 2. So we need twice as much resolution in order to be able to resolve the eigenvalues. So that's why we're going to begin by generalizing this. Recall that the Hadamard operation is the 1-bit discrete Fourier transform. Okay, and so now if we need twice as much, we can end up saying, okay, well, let's take our inputs to be 0 and try to generalize this by taking a f 2 to the 2. Now, instead of having one control, we are going to do this by having two controls. And we're going to invert the Fourier transform. So the difference is that, yeah, actually, never mind. So this is our circuit over here. And now let's pay attention to what this does. So if we recall, F4 acting on 0, 0 is equal to 1 over 2 sum of k e to the 2 pi I 0 k over 2 to the 2 k. Oh, and by the way, this actually also happens to be the same thing as Hadamard acting on 0, 0. So often when people are doing these circuits, they actually don't represent the Fourier transform over here as a Fourier transform, because they can get by with doing the equivalent Hadamard transforms here. Okay? However, I'm not typically going to represent the Hadamard trick like this, because although it's less expensive to do it this way, I think it's a little less clear than it was in the original form where I put the f2 to the n in place of those Hadamard transforms. But in any case, this is the state that we end up getting. We end up getting 1/2 sum from, I'll write this as K1 and K2, K1 and K2 over here. Now let's assume that this is 1 down at the bottom. 1. Now applying the controlled S gates to it, we end up getting this is 1/2 sum over K1. Great. I'll call this value down here K1, and this one up here will be K2. So if we do that, then we end up getting that this is e to the 2 pi I K1 divided by 4 times 2, because it's s squared, K1 times e to the 2 pi I k2 over 4 k2 1. Okay, grouping these things together, this ends up giving us the sum over k 1/2 of e to the 2 pi I over 4 times binary expansion of k, acting on k1. Now we're going to do the exact same trick that we did before. Right. So doing the exact same trick, this is f4 acting on 0, 1, 1. And this is equal to, this, when we apply f4 inverse, is equal to 0, 1, 1. Now note that the exact eigenphase is e to the 2 pi I over 4 equals e to the 2 pi I times 1 over 4. And that's what this ends up representing. In general, if this string over here, it was x, then the phase would be e to the 2 pi I x over 4. So this ends up giving us a way of taking the eigenvalue here and storing it in this phase. So that is how the trick ends up working for this case. Now, let's generalize this. So we've seen some intuition for how the quantum Fourier transform can end up estimating eigenvalues of given inputs. So I'm going to assume, this is the generalization of it, I'm going to end up assuming that we end up having uv is equal to e to the I 2 pi m divided by 2 to the k v for integer m. Okay, now this part is very important because we're actually making a further assumption that ends up generalizing all the cases that we had previously. The previous cases ended up having some rational multiple of pi as their phase. And here we're using exactly the same structure. And the reason why we're going to want to do that is because we're going to want to end up relating these shifts to phase shifts that we end up getting in the QFT circuit. So the way that we are going to build our generalization in this case is that if we have that the phase is of this form, then we're going to need k bits of precision to represent the phase in a form like this. So our quantum circuit is going to begin by having 0 all the way down, 0, 0. So it's going to have k bits here. Then what we do is we feed that through a k-bit discrete Fourier transform. And then we apply a controlled U-gate, acting down on this input state v, which again is an eigenvector of this unitary transformation u. So next thing we do is we do a controlled u squared, just like we did in the previous case, going all the way up to u2 to the k minus 1. And then we are going to apply the inverse, of course, like we always do in the end. And then my claim is that this part over here, if we were to measure it, would give us an estimate of the eigenvalue as a bit string. Okay, so cool. Let's see exactly how this ends up working. So let's assume that V is precisely of this form. So the first step that we end up getting is we have 0 tensor K, V as input. We do the Fourier transform to that, and this ends up giving us 1 over root 2 to the K, sum over K, K, V. Now, this over here is actually just the same exponentiation circuit that we had before. So this, acting under this phase block that we have up here, ends up yielding 1 over square root 2 to the K, sum over K, oh, sorry. There's actually a degeneracy here in my notation. So let me change that variable in here to sum over x. Okay, so I'm summing over x. Now, this ends up giving me, when I use the binary exponentiation trick, this is e to the 2 pi I m x over 2 to the k x v over here. Now I've used two facts. I've first used the definition of the eigenvalue over here, and then I've just used the definition of the binary expansion of x in order to see that when I do all of these controlled operations, I'm going to end up getting not just m up here, I'm going to get m times x, because these over here are representing a binary expansion of x. So this is what I end up having. Now I'm going to do the exact same trick that I always do with these things. This is equal to f 2 to the k acting on a state m times v. And so now if we apply f2 to the k inverse to this, we just end up getting m and v. So if we were to measure these top bits over here, then with 100% probability, what we would end up getting is we would end up getting this bit string encoding m. And from that value, we can actually work backwards and figure out what the eigenphase is, because the eigenphase is just e to the 2 pi I m over 2 to the n. Awesome. So that's how phase estimation ends up working. And next time, I'm going to go into some greater detail about what ends up happening when this assumption that the phases end up being an integer multiple, or sorry, a rational multiple of pi isn't held. So to get to spoiler alert, what's going to happen is that the success probability in this case was 100%. If we don't assume that this is an integer up here, our success probability won't be 100% anymore. However, we can end up making the success probability as high as we want. So once we've got that, I'll go through the rest of that and show how you can perform trade-offs between the success probability and bits of precision as a function of the number of gates that you want to do in order to learn an eigenvalue. And again, why do we want to learn eigenvalues? Well, it turns out that if you take a look at the problems in simulating physics, one of the biggest ones is actually learning the eigenvalue of this object called a Hamiltonian, which is a energy operator. Sort of gives you the energy of a configuration for a quantum system. And quantum phase estimation gives you a way of figuring out what the minimum energy configuration is for a particular quantum system, which is a task that's computationally incredibly hard to even verify on a classical computer. But a quantum computer can verify that straightforwardly. So this is one of the things that ends up leading to potential exponential separations for simulating problems in chemistry as well as the physical sciences. This technique is also widely used in Shor's algorithm, and it's also been frequently used in algorithms like the quantum linear systems algorithm and other applications. And so this approach to quantum phase estimation is very, very useful, also because of the fact that since it doesn't require measurement, it can actually be used inside of other quantum subroutines, whereas iterative phase estimation typically can't. So that is why this is cool and where we're going to be going next time with this. Once I've shown you how we can do this, then I think that'll start beginning also giving you a bit of a primer on how we can move forward onto our next subject, which is beginning to actually look deeper at quantum algorithms themselves and begin to move towards quantum search. Thank you very much, and see you all next time.